So we are officially on spring break. The way my university does things is that we have these moving holidays that the university can move around to help make spring break, winter break, or fall break longer, which is pretty nice. These moving holidays are usually like President's Day, Columbus Day. I'm not entirely sure what all is considered a moving holiday, but I know President's Day is because we did not get that day off earlier this semester. So what ends up happening is that we get a really long spring break, but it comes like at the end of March. So we end up doing like 10 weeks straight with 10 weeks straight with no break. No 3-day weekends, which is kind of rough. Last year it was pretty rough, but this semester I'm feeling pretty good. I got a lot of energy. So I feel like I want to get back into research and just do a bunch of research over the break, because we've kind of switched gears a little bit with me and my advisor. We were looking at this problem. I think I mentioned it in a previous video, like topic of my dissertation or something. And we were working on it, and I feel like we've made some pretty good progress on one of those problems, but I think the rigor isn't there. It's all heuristics at the moment. And I want kind of a second opinion on it too. I need give the problem a fresh set of eyes. So I actually text messaged my thesis advisor and I said, hey, would you be interested in seeing something that I've been working on with my advisor? And he said, yes, absolutely. So tomorrow, I believe, I'm going to FaceTime him and show him what I got, and hopefully he'll say something interesting. I mean, he always does, but you know what I mean. But that's what I want to do over break. I also want to, it's supposed to be a break. I do want to relax. I've been working really hard. This week in particular was pretty rough in terms of, workload. I also need to do like 2 more homework problems to get an A in my Fourier analysis class. So hopefully I'll get something proven over, 1 homework problem done. I'll settle for 1 homework problem at this point. Those homework problems that are left over are pretty tough. But I want to do 1 of them, and I want to make more YouTube videos. I really want to start doing the measure theory series of videos. I did take the notes, and I made the schedule and all that stuff. In fact, these notebook pads I have up here are the official measure theory series of video notes that I'll be using. I think I'll give like the series title a cute name like Measure Theory and Chill or something, because it's supposed to be relaxed. It's not supposed to be super duper rigorous, but I do think I should prove stuff, at least to some extent. So I'm going to try and force myself to actually sit down and do it, and hopefully over the spring break I'll get something done. I have actually filmed 1 video of it. I just didn't upload it to YouTube. But that's on the horizon. That's what I want to do. I teach trigonometry also this semester, and recently I gave them their 2nd exam, and the average was pretty good. They did like 70%. I think that was the class average. But some of them didn't do as hot as I wanted them to, so what I did was I created a extra credit assignment for them to do over the spring break, because some of them had requested it. The extra credit assignment is a little challenging because there's some calculus in it, but it develops the calculus. Like, I'm not just saying, okay, so we know what derivatives are and this is what I want you to do with them. That's not what I did. I really just kind of made a worksheet that walks them through the construction of it, because I know that they've taken a pre-calculus class before, so they have some idea of how the derivative is defined. So hopefully I did a good job of explaining to them what it is I wanted them to do. There's a lot of hand-holding in the worksheet, because I do want them to finish it and actually do it. Because a lot of my students, I did a poll of them and said, figured out how many of them will take calculus 1 and 2. And there's a good bit of them that do need calculus. So my goal, I guess, is with this worksheet is that they'll become familiar with the derivative enough to a point where when they go into Calc 1, they'll be like, oh, I remember that from that worksheet from last semester. That is, at the very least, my hope with the document. But, if they get stuck, I told them they could email me and I would help them. But I really want them to do it themselves. So hopefully that will keep them entertained for a week. And, yeah. So earlier this week, which is what I want to talk about in the remainder of this video, is that on Tuesday, my instructor for the Fourier analysis class was not there, which means that the substitute that was there, which just so happened to be my advisor, he gave us a pop quiz. And the pop quiz is that we had to prove I'm going to butcher the name, but it's the Marinko interpolation theorem. And I like this theorem because it was one of these proofs that when I saw the first time, I pretty much understood every step that he went through. And, most of the time that doesn't happen. Most of the time I just need to review the proof over and over again before it starts to sink in. But this proof kind of made a lot of sense to me when I saw it the first time. And on the quiz, I'm pretty sure I got at least 95% of it correct. There was one step where I was, at a loss for details, but I don't think it was that big a deal. I was able to remember the vast majority of the proof. So that made me feel pretty good about myself. Sorry, my voice is leaving me. So I thought I would go through the proof of the interpolation theorem and, walk through it myself just to see, how much of it I do remember. I wrote this up right before the video, obviously. So what does it say? You have two real numbers, P0 and P1. They are distinct. And P0 is bigger than or equal to 1. P1 is bigger than P0. And P1 we can assume to be equal to infinity. We have a linear operator defined on the set L1 intersect L infinity x. So L1 is the space of integrable functions over x, and L infinity is the space of bounded almost everywhere functions on x. And then we intersect the two. So t takes a function that's here and it maps it to a function in the same space. And it's a linear operator. We assume that the mu measure of the set of all points in x, but this is just shorthand notation, set of all points where the absolute value of tf bigger than t, where t is some real number, is bounded above by some constant cq, depending upon q, where q is p0 or p1. So we're kind of doing two things at once here. We're saying, okay, this set is bounded, the measure of this set is bounded by some constant depending upon p0 or p1, times the LQ norm of f raised to q divided by t to the q. And this is kind of like, if you think about it, how should I describe it? It resembles the, the weak type 1-1 bound, or I guess it's not, hold on, I want to make sure that I don't say anything that's wrong, because I've been watching some of my old videos and I've been really screwing things up. But you can see the connection between this and the weak type 1-1 bound, or even like the Chebyshev inequality. Like there's similarities between the two. So this is the bound that we are assuming. If q is equal to infinity, which I should mention here that p1 is finite. So in the case where p1 is infinity, we can assume the weak type infinity bound. So in the proof that I'm going to show, I am just going to do the p1 finite case because the infinity case was given to us as a homework problem. One of my friends did it. The proof is very closely related to the proof given here, and it just needs to be adapted a little bit. So we'll just do the p1 finite case. So given this assumption, we want to prove that for any p between p0 and p1, that the operator t, so this operator t from LP to LP, is finite. So we have a bounded linear operator t. Okay, so how do we start the proof? So the proof actually requires a lemma, and this lemma was actually given to us as another homework problem. And the lemma is this claim that follows here. So what do we need? We need a mu measurable function g. So g is a measurable function defined on x. It's non-negative. And we have this function phi from positive or non-negative to non-negative real numbers. We assume that it is convex, differentiable, and that phi is 0 is equal to 0. From my notes in class, I'll tell you this much. He did not write this line. I had actually got up and left to use the bathroom, And when I came back, all he had written was a picture. But I didn't want to write the picture. What we really need, though, to be honest with you, is like phi of t is equal to t raised to the p power. That's really all we need in this case. But when I looked at the picture that he wrote, I was like, all right, F it. We'll just write it this way, because this is basically what he had drawn, written in the English language. So we have that. So what is the claim? The claim is that the integral of phi gx d mu over the space x is equal to the integral from 0 to infinity of phi prime t times the mu measure of g bigger than t dt. And he actually proved the claim for the sigma finite case, where mu is a sigma finite measure. And the homework problem was to show that this is true regardless if mu is sigma finite or not. In fact, that was actually the homework problem that I did up at the board, because it was a fairly simple proof. Okay, so we're just going to assume that we have the claim, this lemma, and we'll apply it later. We're not actually going to prove it. So we're going to fix a p between p0 and p1, and we're going to let f be an LP function. All right, so our goal now is to show that t is a bounded linear operator, and one way that we can do that is to show that the LP norm of TF is finite. In fact, what we're actually going to do is take the LP norm, raise it to P, and show that is finite, because then you can just take the 1 over P power, which is what we have written here, and if we show this, we have this, and if we have that, we'll have this. So that is our goal. The trick that we do, or that we use, is that for a positive real number t, we are going to take the function f, and we are going to basically decompose it. So we have f sub t and f super t. F sub t is defined as follows. So f sub t is going to coincide with f when the absolute value of f is bounded above by t. So you can think of this function ft as like, you have this, like if you have the xy coordinate plane, you have this window of height 2t, and that if you are inside the window, f sub t is going to match f, and then whenever f goes above or below this window, we're just going to kill it and set f sub t equal to 0. So it matches f inside the window. And then f super t is going to do the opposite. It's going to match f when you're outside the window, and it's going to be killed when you're inside the window. So that's f sub t and f super t. Okay. Let's fix this. All right, so hold on, this is going to bother me. I know, real professional setup we have here at SGS Studios, but at least we have the math, right? Okay, so this is the claim. If we have the claim, then basically the whole thing is proven. So we write this norm in its form here. So this is this written out explicitly. We want to show that this integral is finite. So we use the lemma. So remember, phi is our function t to the p, essentially. So we've composed tf inside that function. So that's what's written here, which means that if we apply the lemma, we can rewrite it this way. So this is our derivative of phi, so to speak, and this is our mu measure of that function g bigger than t. That's how the lemma is applied here. And now what we're going to do is we're going to find something bigger than the mu measure of this set. So we can decompose tf into tf sub t and tf super t, and essentially by triangle inequality you can replace the inside of what we have written here with this guy. So this is greater than, or excuse me, this is less than equal to this guy, where we just replace tf with these two values. And then what we're going to do now is split this set up into two other sets and take the measures of those two sets. So we're interested in the case where tf super t is bigger than t over 2, which is written here. And we're interested in where tf sub t is bigger than t over 2, and place that here. This decomposition, where we take this set and split it into two smaller sets and measure them, did not really make sense to me the first time I saw this trick. And then I realized, I don't know if I came up with this or someone told me it, but the way that was described to me is that if you have an apple and you cut the apple into two pieces, at least one of those two pieces is bounded below by half the size of the apple, if you think of it that way. Like, you can cut the apple directly in half, or you can like shave off just a tiny piece of the apple, but then the other piece of the apple is just massive. It's definitely bigger than half the apple. And that is essentially what this is, metaphorically speaking. Okay, so now we've split this. So now we've split this set into two pieces, take the measure of each piece, and now I'm going to, what's the property called? The additive property of the integral, where we're just going to look at the integral over this function and then distribute this function over here and then take the integral of that. So now I've taken one integral and written it as two integrals. And now I'm going to play with each integral. We denote the first one as I1, and we're going to denote this guy as I2, and we're going to show that both of these integrals are finite. And if we do that, we're done. We start with I1. So in I1, we have Tf sub t, and with this measure, we can apply our original assumption. Our original assumption is here. So we have Tf sub t is bigger than t over 2. And the norm that we want to play with is P1, because remember how TFT was defined, or rather FT was defined. FT was defined with F being inside the window. So we want to measure it with the larger of the two p's, or we want to bound it with the larger of the two p's. So using that assumption, we can replace this guy with this guy. So this is our constant depending upon P1. This is our LP1 norm raised to P1 over T over 2 raised to P1. Because remember, T over 2 is playing the role of T in this case. So it's really T over 2. So we have this integral. We can combine a few things. So the 1/2 raised to P1 power, we can throw that in with this P that's out in front, with this CP1, to create a new constant called CP1 prime. And we can pull that out of the integral. And then we have T raised to the P1 power, and we can combine it with this T. So we end up getting this integral. CP1 prime integral T to the P minus 1 P minus P1 times this LP1 norm raised to P1. That was a mouthful. It's easier to write up than to explain in words, I do admit. So bear with me for a second. So the next step is I like to explicitly write out what this integral is, and that's what we have written here. So notice that ft coincides with f when f is bounded above by t in absolute value. And outside of the integral, it's equal to 0. Or excuse me, outside the window, ft is identically 0, so it contributes nothing to the integral, which means I can restrict the domain to just this set and replace it with f here. Okay. And now we can move some things around. And what we can do now is integrate f, the absolute value of f raised to P1, over the whole space X, but this time we restrict T to the set where T is bounded below by absolute value F. And when you compute this integral, and this is just an honest integral, because you can just use your old school Calc 1 skills to add 1 to exponent, divide by new exponent, and substitute where appropriate to write this as absolute value F raised to P minus P1 power over P1 minus P. And this is just a constant that's downstairs. So I can pull that outside of the integral. And then this guy can be combined with this guy. So we add the exponents and get absolute value F raised to P, which is what we have written down here. And then what do we have? we have constant out in front, and this is just the LP norm of f raised to the p power, which I substitute here. And we assumed from the very beginning, well, not the very beginning, but we assumed here that f was LP, which means that this LP norm raised to p power is finite. So we have constant times finite is definitely finite. And that proves that I1, that first integral, is finite. And then you have to do essentially the same thing for I2 with some slight modifications. So I'll just go through it pretty quickly here because it's almost exactly the same. You do the substitution that you have, except now we're going to play with P naught. So we do the same substitution that we have from the very first assumption. You can combine some constants to make a new constant, C prime P naught. Combine like exponents, do all that good stuff. Identify our domain of integration, move some stuff around. Evaluate the integral honestly like we had before using a Calc 1 skills. We get this guy. Pull out the constant. Combine the exponents. We get this guy, C prime P naught over P minus P naught. And we have the LP norm of f again show up quite nicely, which we know was finite like we had before. So everything here is finite. So because I1 is finite, I2 is finite, you add two finite numbers together, you get finite number. This tells us that our LP norm of TF is finite, so T is a bounded linear operator. And there you have it, the Marcinkiewicz interpolation theorem. I think if you're curious where I screwed up during the proof, during the quiz, I think I forgot temporarily what the domain of integration was in this integral. But I knew what it kind of looked like, so I just made a comment like, okay, we know that it looks something like this, so don't get mad at me too much, Mr. Grader. But yeah, it's a nice little theorem. My advisor said that he used it once when he was writing a paper, and I just like the proof of it. I understood it when I saw it the first time, so hopefully I was able to explain it in a reasonable manner.